Good evening. Welcome to the USGS public lecture. My name is Mitch Adelson, and I will be your host and moderator today. Before I introduce our speaker, I have just a few announcements to make, and this will allow others out there in virtual land a few extra minutes to get logged in. First, I would like to give you a heads up about our lecture for next month. On March 24th at 6 p.m. Pacific time, we will have Matt Kaufman with the Wyoming Cooperative Fish and Wildlife Research Unit talking about hoofing it in the West, conservation challenges, and solutions for migratory big game. So please be sure to save the date and join us next month as well. At the end of the lecture, I'll provide information on how to join our mailing list so you'll always know about our upcoming lectures. And next, we want to take a second to give you some tips on some of the features on this Teams platform. If you're watching this on a desktop computer and need to turn on closed captioning, please look at the bottom right-hand corner of the screen for the closed caption icon. That's the one with the two little C's. Another feature we would like to direct your attention to is the question and answer panel, which can be opened by clicking the question mark icon in the upper right-hand corner of the screen. At the end of the lecture, we will have a Q&A session, and this panel is where you can submit your questions for our speaker. Please understand we may not have time to answer all the questions that come in, but we will do our best, and we appreciate your understanding in advance. And now it's time to begin our lecture this evening. Tonight, we have the pleasure of welcoming Dr. Zeno Levy. Zeno earned his Bachelor's of Arts at the New School University in New York City and went on to earn his MS in Environmental Science at SUNY ESF and a PhD in Earth Sciences at Syracuse University. Zeno worked briefly for the state of Vermont as a source water protection specialist before joining the U.S. Geological Survey in 2018 at the California Water Science Center in Sacramento, California. Zeno is a hydrogeologist and geochemist and works primarily on the State Water Board's Groundwater Ambient Monitoring and Assessment Program, known as GAMMA. So without further ado, let's all give a warm virtual welcome to Zeno. The floor is all yours.
Thanks, Mitch. And please excuse my messy desktop as I load up this presentation. Okay, well, thanks again to Mitch and the organizers of this lecture series. Certainly a very storied series, and it's quite an honor and a privilege to present and add this story to the pile. So let's jump right in. I first want to acknowledge that some of the work I'm going to present today was funded as part of a cooperative agreement between the U.S. Geological Survey and California State Water Resources Control Board as part of work done for the Groundwater Ambient Monitoring and Assessment Program, GAMMA, more on GAMMA later. And additional thanks to folks within and outside of the USGS who have helped along the way developing some of the ideas that I'm going to talk about today. Groundwater and drought in the West is currently a very hot topic. And this is a familiar headline people might see popping up on their dashboards. California and Western US could see increased drought risk. And it seems like it's always getting worse. And farmers are upset about it and concerned. And you also tend to hear about groundwater and that people are drilling in these things called aquifers and they're pumping water out, but the water's running out. And these droughts are scaring people because they think their wells are going to run dry. And in some cases, wells are running dry. And people are really concerned, and there's a lot of technology and effort being put into this, but wells are still drying up. And I kind of like this article because there's a picture of a woman hugging her pressure tank in it. So I want to whisk you away to California's Central Valley, an extremely productive agricultural belt in the center of the state. And I want to, this is a map showing in blue domestic household wells throughout the Central Valley. And the red points represent wells that were reported to have failed or to have gone dry during the last previous major drought from 2012 to 2016. And you'll notice that these wells are mostly located in the lower 2/3 of the Central Valley, also known as the San Joaquin Valley. So these the clusters of red points you see are mostly located in the Tulare region of the San Joaquin Valley, and there were a lot of news stories during this last big drought about wells going dry in places around Fresno and Tulare. One of the towns that was focused a lot on was East Porterville, where bottled water had to be shipped in because people's wells were going dry. So what actually is happening when people's wells are going dry and they're reporting dry wells? Well, we can think of groundwater as basically, there's no magical underground river. It's basically just water filling up the sandbox of the earth. And straws poking down into this sandbox, you can think of wells as kind of straws sucking up water from the saturated earth through perforated openings known as well screens, shown here in this diagram, and pumped up to the Earth's surface for use using well pumps. So in this diagram, we can see that the water that the sandbox is filled up to can be termed the groundwater level, and it's indicated by this upside down blue triangle. So during droughts, water levels, the sandbox water level can actually lower, and if it falls beyond where the straws are sticking into the earth and pumping from, that well can go dry and be termed a failed well. So I want to talk about water quality today, and I want to, but the connections between drought and water quality are actually a lot murkier and less clear, excusing the many puns that I'm going to be employing today. But, you know, this is a picture on the right of some water that was pumped out of a filling well, agricultural well in an orchard in 2020, which was a very dry drought year. And, but, you know, this is kind of the most dramatic, visible way to see this problem, but really it's kind of actually a much more hidden and invisible problem, because often contaminants in groundwater, such as nitrate, which I'm going to talk about a lot today, are tasteless, colorless, and odorless. So it's a lot less dramatic than someone's well going dry. But actually, when people were surveyed in the Fresno and Tulare regions of California, where a lot of these wells were going dry during this big 2012 to 2016 drought, a lot of the respondents indicated that about 70% indicated that at least sometimes they felt that the drought was impacting the quality of water in their households, which so there's been anecdotal evidence that's built up around this question, but it's been more of a sticky wicket than one might expect. So here is the big question: do droughts affect groundwater quality? And the answer is, well, it's complicated. And one of the reasons it's complicated is that conventional wisdom has shown is that groundwater quality is thought to be slow to respond to changes at the land surface. And the reason why this is when a groundwater hydrologist does think about where groundwater is coming from, but we also think about when groundwater is coming from. And in this schematic, you can see As we peer deeper into the earth, we find older and older and older groundwater. And this is actually, we know how old groundwater is because we can use isotopic age tracers to actually date at what point the water percolated down into the earth. So in the shallow parts of these groundwater, this groundwater sandbox, the groundwater may have entered the earth and built up under the earth on the scale of days to years. But as you go deeper, especially to the depths that a lot of drinking water wells are drilled, especially in California, you might find the groundwater has been sitting there under the earth for decades, centuries, even millennia. So this kind of begs the question, how can drinking water resources from deep underground that we've actually been able to quantify as being decades to millennia old be affected by California droughts in the past several decades that typically span 2 to 5 years? So I want to attempt to answer this question today to resolve this mystery, but I actually don't want to just throw a lot of science at you. I want to tell you a story, and I want to tell you a story about California and how California experiences drought, and how drought affects its $50 billion a year agricultural industry, and the impacts of drought on groundwater depletion, and ultimately identifying this linkage that I want to put forward between groundwater depletion and groundwater contamination in this hugely productive agricultural system. But first, I want to take you to USGS Water Science School. And I want to talk about groundwater budgets and overdraft fees. And so the analogy I want to make today is thinking about groundwater filled in the sandbox of the earth, which we call an aquifer. The groundwater as being kind of imagining that as you would a bank account that you can draw from as needed. And the water table, the upper surface of where the water has kind of piled up in the sandbox of the earth, is actually a really good indicator of your balance in your bank account. So when it rains or you irrigate the landscape and that water percolates down into the earth and reaches the water table and builds up there, we can think of that as putting a deposit in your bank account, and hydrologists like to call that recharge. But what happens is the water percolates down and water levels rise up, and you have more money in your bank account to draw from later. Now, when we pump a well, we can think of it as withdrawing from our bank account, and when this happens, there's actually the water level, which is kind of showing the balance of the bank account, can actually get lower down into the earth, and we call that, as hydrologists, drawdown. Now, around pumping wells, we tend to see these cones of depression, which are kind of depressions in the water table surface. You can imagine drinking a milkshake up through a straw and seeing the water get sucked down around the straw. But to extend the analogy a little, imagine you have to pay your rent and you have to withdraw from your bank account, you might see a little depression in your balance. You might see your balance go down a little, but you know you're getting your paycheck at the end of the month, everything will balance out okay, and your budget's balanced because you're a very responsible human being. So this drawdown, this cone of depression around wells can kind of be transient. But when we overdraw and we overdraft our bank account and we start taking out more than we're putting in, you can think of that like pumping out much more than is recharging down into the groundwater. And you can actually get more long-term chronic drawdown of water levels that aren't just around the well, but are kind of regional. And you might end up like Sad Banker, with mountains of debt and chronically dropping water levels. Well, groundwater depletion, this idea of being out of balance or overdrafted, is actually a global problem, and it's imaged here as globally in kind of this cool figure showing mountains of groundwater depletion rates. So we can see that groundwater depletion rates or deficits are pretty high in places like Southeast Asia and East China Plain and the Middle East, and also the Western United States. And I just want to highlight, groundwater is being depleted because groundwater is actually a really important resource. Drinking water, groundwater supplies drinking water to over 1.5 billion worldwide and makes up almost half of the water used for irrigation worldwide. So it's a finite and precious resource, and it is being depleted in certain areas rapidly. And this hits home locally when we actually look at the United States. And so this figure shows groundwater extraction rates with higher rates being kind of darker colors. We can see that groundwater extraction rates are pretty high in the Western US, especially in areas supporting irrigated agriculture like the High Plains aquifer, and in the Southwest, especially California. So let's go to California. Welcome to California's Central Valley, shown here in the middle of the state, America's breadbasket. It's a long, narrow valley that with very fertile soils, and it's been made so agriculturally productive by the benefit of being right next door to a mountain range which provides stream flow to irrigate the entirety of the Central Valley. And this stream flow is distributed throughout the Central Valley with a complex conveyance of water distribution infrastructure, including reservoirs and dams and canals that spread across the landscape. And this in total supports a $50 billion agricultural industry statewide, and the Central Valley is a major chunk of that revenue. And I'm definitely dating myself with this corny 90s reference. So it seems like a great situation, but then along comes drought. And this figure is very busy, don't worry about it. It's just showing there's so many different types of droughts, and there's so many different effects of droughts, which range from disappointed hikers to everything is on fire. But the point I want to make here that's apropos to California is that during extended droughts, there's actually less stream flow out of the mountains to go around to help support irrigation of agriculture. And in the Central Valley, we have seen, it's been observed that the Central Valley is being overdrafted, the groundwater is being overdrafted, and that there's a very close interplay between climate and surface water deliveries to the Central Valley, shown here as green bars, and groundwater storage, shown here as the downwards trending red line, which looks eerily like Sad Banker's chart. But what we can see through this interplay, this red line is really what's in your bank account, what's in your storage of groundwater. And what's apparent is during wet years, shown here, when there's plenty of surface water deliveries, groundwater storage actually increases. People are irrigating the landscape, and some part of that irrigation water is going to fill back up the sandbox, if you will. But during dry times, surface water deliveries diminish quite a bit, and farmers rely more on groundwater to get them through the dry periods. But this results in this overdraft and this decline of groundwater levels in storage. And this has actually caused most of the San Joaquin Valley, circled here, most of these little groundwater basins in the San Joaquin Valley have been termed by the state of California to be critically overdrafted groundwater basins. In other words, they're racking up debt left and right, and their water levels are declining. Just one point here: the upper third of the Central Valley is known as the Sacramento Valley, and it has not shown signs of this overdrafting or this racking up of debt. And that's generally because the climate's a little wetter up north there. And they tend to get more surface water allocations than the San Joaquin Valley, where surface water deliveries can be very restricted when the streams start to dry up during drought. The most dramatic kind of visible effects, because groundwater is very invisible, it's under the ground, but in the San Joaquin Valley, this is kind of a famous picture of, if you've ever seen land subsidence talked about, this is the picture. And so the land surface was up here at the top of this telephone pole in 1925 and settled down to 1977. That's because in areas where tons of groundwater have been removed from the earth can actually compact and settle down. So it's kind of a very visual example of the extremity of some of the groundwater withdrawals in the San Joaquin Valley over time. So to intervene in this unsustainable situation, the state of California passed the Sustainable Groundwater Management Act, or SGMA, in 2014. And the purpose of SGMA was to create local groundwater management agencies to kind of try to balance the groundwater budget locally and try to manage pumping and recharge operations locally throughout California. And this schematic just basically shows in SGMA, there are undesirable results and that are listed as part of the management scheme. And one of the biggest ones is that people are trying to manage their way out of are falling groundwater levels and this idea of overdrafting. So ideally for SGMA, that these groundwater sustainability plans, or GSPs, would be adopted, and a lot of them were submitted in 2020. And then as management, that there would be more management of pumping operations to try to get things back in balance and kind of stem the decreasing water levels. But so one of the undesirable results in SGMA is that's listed in the plans that people have to put together to manage the resources, is that people have to talk about water quality and think about the sustainability of the quality, not just the quantity of their groundwater. But up until recently, a lot has not been really known about how to do that. And today I want to shed some more light on the water quality aspect of this management. So what's water quality got to do with sustainability? And I would put forward a lot. This schematic shows common sources of groundwater contamination, and I just want to orient people to kind of what we mean when we talk about groundwater contamination and different types of groundwater contamination. So on one hand, there are what we call point sources of pollution. So that would be a specific place where kind of nasty things, contaminants, are seeping out of maybe a landfill or a septic system here, and they're kind of seeping into the groundwater, and then they're kind of moving in the direction that the groundwater is moving, and they extend out in these kind of these long, narrow areas that are called pollution plumes. And although this is very big for illustrative purposes on this plot, plumes actually are pretty limited in extent. They tend to be on the landscape. But on the other hand, there's non-point source pollution, which is more spread out on the landscape, and it can be from agriculture or roadways, pollutants that wash off into the ground, and they kind of spread out over the landscape in a cloud, and you can't really pinpoint where exactly that contamination came from. It's kind of all over the place, maybe. And that is actually what I'm going to focus on today in the context of California agriculture. But I also want to just mention that there are natural sources of contamination that can affect groundwater quality. So sometimes deep in the earth, from minerals in the earth, you can get water with high salinity or metals such as arsenic or chromium. And that's also something to keep in mind when we think holistically about groundwater. So I want to talk a little bit about some of the work we've done at USGS to try to look at groundwater quality through the state of California. In this program, the Groundwater Ambient Monitoring Assessment Program, it's been around for almost 20 years now, and it's a cooperative agreement, as I mentioned, between the USGS and the California State Water Board. And so the purpose of GAMA is basically to sample wells and test the water for all kinds of things, from agricultural contaminants to pH to some of these isotopic age tracers, which I'll talk a little bit more about in a bit. So we can build a picture of where are there areas of better or worse water quality throughout the state, and what might be the cause. We're not just satisfied with where there might be contamination, but also what are the sources of contamination, and why might areas have better or worse quality of groundwater. And we also want to get at well, what are the trends, and how are things changing in time? It's not static, it actually changes in time. So in this big monitoring program, we actually look at groundwater resources from two different perspectives. We look at domestic wells, which are privately owned household wells. We also look at public supply wells that are wells that service larger populations. They can be municipal, city wells, wells that service schools or trailer parks, and it's actually defined by usage, not ownership. So some differences are domestic wells tend to be, especially in the Central Valley, shallower and screened over shorter portions of aquifers. They're not regulated. You're not required to test your water if you have a domestic well. We provide a service for science to test water, but people are free to use their own privately owned wells as they wish. And in the Central Valley, for context, there's about 67,000 domestic wells, servicing a population a little over 500,000. In contrast, the public supply wells tend to be deeper, have much longer screens, and they're pumping more because they're servicing bigger populations, not just one little household. And they are, because they're servicing large populations under the Safe Drinking Water Act, that they have to be periodically tested for water quality. And and to put in, again, context of the Central Valley, there's much fewer public supply wells, only about 3,500, but it services a much bigger population, over 3 million people served, in contrast to the domestic wells. And, so these wells are very different. The domestic wells might yield something like 15 gallons per minute or so, while public supply wells are pumping much more to service larger populations, and they can be going at rates of 500 to 1,000 gallons per minute and upwards of that. So two very different types of resources. So now I want to hone in on water quality concerns in the Central Valley and this cloud of nitrate that's been observed in the groundwater throughout the Central Valley. So nitrate is, as I mentioned, a colorless, tasteless, odorless contaminant, and it's actually a nutrient that's derived from fertilizer use. So all of the agriculture in the Central Valley over many, many years has caused there to be a lot of transport or leaking of this nitrate contaminant into groundwater. And the gamma data and other USGS data has been used to kind of map out the levels of nitrate, both in shallow parts of the Central Valley groundwater that is tapped by mostly domestic wells, and the deeper portions of these groundwater aquifers mostly tapped by the public supply wells, and with these darker colors indicating higher and higher levels of nitrate. So we can see nitrate tends to be a lot higher in the shallower groundwater nearer to the surface, and lower in deeper groundwater, but still prevalent really throughout much of the Central Valley. And I'm going to focus on nitrate in this talk mostly because it's a really good indicator of kind of agricultural pollution coming from agriculture. But I just want to mention it's found with fumigants, which are a type of pesticide and other agricultural chemicals. So it doesn't always come alone, but there's a lot of data for it. So we can really paint a picture using nitrate of the extent of pollution from agriculture and groundwater. And it's a threat to drinking water supplies because there are health risks associated with nitrate levels above 10 parts per million, which is kind of the safe drinking water level, or what we call maximum contamination level, MCL, which is basically above which it's not really safe to be served to the public. And there's health impacts associated with this. And also, wells really can't be publicly serving groundwater or shouldn't be publicly serving groundwater with these high levels, shown here by the darkest colors. So how did things get to be this way? Well, the answer is that people have been loading fertilizer on the landscape, which has been seeping nitrate into the groundwater for years. And you can see in this plot, the blue line shows applications of fertilizer in the Central Valley from the 1940s up through the early 2000s. We can see that relatively low application rates in the 40s increased dramatically in the 50s, 60s, 70s, 80s, and onward as population shown by this green line increased in the Central Valley and agricultural operations intensified. So when we peer into the groundwater below the Earth's surface using age dating tracers, we can actually look at both the concentration and the levels of nitrate and how old the groundwater is. So here we show these points are areas that the USGS sampled groundwater below the water table. And we can see the blue points are kind of ambient low background concentrations, and the yellow and red points are elevated concentrations of nitrate, the red being the highest concentrations of nitrate. So when we look at the deepest part of this area, we've actually used age tracers were used in the study to delineate that these 4 points with really low nitrate values were aged pre-modern water, which means pre-1960s, so a time when fertilizer applications were really low. But as you go up through this groundwater system, you see higher nitrate values are associated with water that actually moved down into the ground surface, recharged, put into the bank in the 60s and 70s and 80s and 90s when fertilizer applications were higher and higher and higher. So we see this relationship between nitrate and groundwater age, which is consistent with what we've seen throughout much of the Central Valley. So this kind of explains why the domestic wells, the shallower wells, had much higher nitrate in the previous plot, because you can see these wells are drawing in water that was recharged in the 70s and 80s and 90s when fertilizer application rates were pretty high. But our public supply wells might be tapping water that's much older when fertilizer application rates were much lower. So even though these nitrate levels are tend to be relatively lower in these deeper wells, public supply wells, that we've been noticing and monitoring trends in the Gamma program. We've noticed, based on the regulatory monitoring data and our own sampling, that nitrate is actually having an upwards trend in a lot of these deep wells. And one well operator once told me when I was out sampling, nitrate is a well killer, because these public supply wells, they have nitrate levels going up, and if it hits above the safe level at 10 parts per million, they really have to either treat the water or close it down, drill a deeper well. And a lot of the times that's not financially possible. It's very expensive, and the treatment is really difficult. So it's actually a real problem. But when we've peered closer at these trends, we've been focusing for a while on, well, is it going up or is it going down? But actually, a smoking gun towards the big question of this talk can be found by peering at some of these trends over time. So you have time here and nitrate on the y-axis going up over time, but some of these time series can be used to connect the dots between how water quality changes during wet periods when we see nitrate levels going down in some of these wells, and what might be happening during droughts when we see nitrate spiking at some of these wells. So this was really kind of looked at when we started noticing this. It was kind of a smoking gun to, hey, maybe there is something to this drought and water quality thing. So I want to bring you to this recent study that came out of the Gamma program, where we tried to kind of finally get at this question: do droughts actually affect groundwater quality? And we had this hypothesis that, well, we know pumping increases during drought and causes a lot of this drawdown and lowering of water levels. Maybe that affects things based on what we know about shallow and deep groundwater. So over here on the left, I'm showing another schematic of the Central Valley, just showing long-term drawdown by these deeper, darker reds, showing that a lot of the groundwater level decline, as we already know, it has been centered in the San Joaquin Valley region. And there's been less overall groundwater level decline in the Sacramento Valley to the north. In this study, we focused on these deep public supply wells because we think that they might be really good indicators, and we have really good records of nitrate, which we focused on in this study, from the regulatory monitoring data that the wells are required to supply to the state. And the location of public supply wells are shown here as higher density wells in these little hexagon grid cells by deeper, darker blues. You can see the public supply wells tend to be clustered around urban areas with higher populations being served. We looked over a 30-year period at water levels change and nitrate, encompassing 3 major regional droughts. And that's shown here by this Palmer Drought Severity Index, which all you really have to know is that here's the year, and as time goes on, the red means it was a dry time, the blue means it was a wet time, and I've highlighted these 3 major regional droughts that occurred over the past 30 years in pink: Drought 1, Drought 2, and Drought 3. So in order to try to figure out some connections between the pumping and the groundwater levels and the water quality, we have all this water quality data from these public supply wells, but we needed to get at, well, where is the water, what are the water levels doing? And one of the unfortunate things is that the places where water levels are measured are often not the same place where the water quality from these public wells were measured, because they're not required to supply water level data. So basically what we did was we made a model of groundwater level change throughout the Central Valley over the past 30 years. And so I'm showing here a time series of depth to groundwater. So you can see groundwater levels in our model go down and they go up and then they go down again here. And they match pretty well with observations at one point in the Central Valley where we had a really good time series of observations. So I'm going to play a little movie here of our model. And so we kind of statistically interpolated between wells where we knew what the water levels were doing to kind of paint a picture of water level change over this 30-year period. So the blue are areas where water level has risen compared to the water level in 1990. And the reds are where water level has declined compared to 1990. And consistent with this graph, you can see that a lot of areas water level has declined over this time period, as expected. So I'm going to throw more plots at you here, but I promise this will all be over soon. But seriously, when we looked at the general water level trends in the San Joaquin Valley over this 30-year time period, we kind of saw something that made a lot of sense with what we know, which is that, water levels tended to increase during wet times and decrease during droughts. So water levels tended to drop pretty dramatically during these droughts, superimposed over a long-term downwards trend, which is like, again, our bank account being overdrawn and diminishing resources. But we found, we had a major finding, which is when we look at the population of wells having elevated nitrate concentrations above half of the safe drinking water level. So shown here, this y-axis is actually the proportion or percent of wells that had high nitrate. We see that during this last wet period, the proportion of wells with high nitrate was actually pretty low, below 20%. And then over this period of long-term water level decline, the proportion of wells that had high elevated nitrate actually reached up to 30% during the last drought and kind of spiked during these droughts. So this was kind of another big sign that there's a linkage here going on. And we also found that the depth to which these wells, we were getting more and more wells over this time period that had high nitrate levels. And the depth of those wells was actually getting deeper and deeper with time, which is what this little line is showing. So we're finding that these wells that are lighting up with elevated nitrate are also deeper and deeper, which suggested to us that nitrate is, over this time period of water level decline, is actually moving deeper and deeper into the earth, below the Earth's surface. In the Sacramento Valley, we found as I noted before, there's been a lot less drawing down. There's been a lot less deficit in groundwater levels, a lot less lowering of the levels. They've been pretty stable with time. And we see lower, and generally lower rates, less than 15% of the wells had elevated nitrate there. And we don't really see these kind of patterns, these droughty related patterns like we did in the San Joaquin Valley. And just looking at this most recent drought period, 2012 to 2015, show the red is where we're getting more nitrate during this drought. That was more prevalent over the landscape. We see more wells with high nitrate during this drought period, but in the couple years after the drought, when water levels stopped falling and kind of started to go back up again, we actually see less wells that had high nitrate. So we're seeing really in real time a lot of changes happening with nitrate related to these drought and wet periods. So one of the big takeaways from this study is we think we put forward pretty compelling evidence that there is actually a linkage here. But droughts can affect groundwater quality, and we propose that we know that there's this shallower, higher nitrate, younger water that tends to overlie this deeper, older water with very little contamination from nitrate. And that during droughts, when there's overpumping and there's a lot of drawdown, it can actually suck down further some of the shallow contaminated water deeper into the ground to the depths that are tapped by these big, very productive wells. But complicated. And I just want to throw in here near the end of the talk that, it's really not one size fits all with contamination. And I just there's more things than nitrate. So this shows in red a conceptual cartoon of salinity. And we can see that actually in some cases, there can be really deep natural salinity in groundwater. And during periods of heavy pumping, there's actually been observed what's called upconing, or water being pulled up from deeper. So there can be, it's really kind of depends on the geology of the area and where contamination is in aquifers, and it really isn't one size fits all. Similarly, it's been shown that wells near coastal areas, when they're pumped very heavily, can draw salty seawater into them. So I just want to highlight that we focused on nitrate in a very specific region with very specific things going on, but there are relations between pumping and groundwater quality for much more broadly, but they can be complicated and kind of site specific. So just kind of getting to the end here, I just want to put forward a question, which is, are these dry wells, which are very visible and people talk about a lot, these failed wells, are they the tip of the iceberg? Remember early in the talk, we saw that a lot of wells were drying up during this last drought, and it actually was about a 3% failure rate of these dry wells. But also, we showed in our results that about 30% of these public supply wells we were looking at that service much bigger populations had elevated nitrate that increased during the past drought. So I just want to stress that it's really important to think not just about quantity and these visible dry wells, but also what's happening with water quality during drought. And I just want one final note. There's something that's being proposed to deal with overdraft and groundwater depletion in the Central Valley is something called managed aquifer recharge. And one of the methods of doing this is flooding agricultural fields in the winter when they're not being actively growing, when there's a lot of more river water to go around during wet times, and actually using that to bank more water and to fill up our groundwater accounts to take people through the next drought. And there has been some interesting studies, particularly out of UC Davis and others, that have looked at how this might actually affect nitrate. And even though these are agricultural fields, some of the early results have shown that just by putting a ton of relatively fresh river water on the landscape can actually serve in some cases to maybe dilute and lower the nitrate levels in the shallow groundwater. But a lot more work needs to be done on kind of figuring out if this will actually affect nitrate that's already in the pipeline, that's already moved into the earth, and if this could somehow maybe be used to mitigate this problem with rising nitrate levels at wells. So final thoughts, I hope I've convinced you today that it's not just the quantity of the resource you think that's available. We also really do have to think about the quality of groundwater as a resource, and that you might think you have a ton of money in your bank account, but maybe, just to keep extending the analogy, maybe you have some frozen assets. It's not liquid, it's not usable, so you might have an inflated sense of what you have. And I hope in this talk I've communicated that groundwater quality is really important. And oftentimes it's actually not murky like this, it's invisible. And it's really helpful to understand the quality of what you have in addition to the quantity of what you think is available. And with that, I'll take questions.
Okay, thank you, Zeno. You covered a lot of great material today. I've been keeping track of the questions that come in throughout your talk, so now's the time for the question and answer portion of the lecture. As a reminder, if you would like to ask a question, remember to click on the Q&A chat window. Look for the question mark icon in the upper right-hand corner of the screen. Okay, Zeno, we had a few people ask about what isotopes you use to determine the age of groundwater. How far back can you age trace water, and how many years or centuries can be dated?
A really good question. Obviously, the age dating stuff is a whole other talk. It's super fascinating. It's something there's been a lot of work at USGS and academic institutions. And I'll highlight just a couple things. There's actually a variety of age tracers. One of the big ones that's used is tritium. And basically, during nuclear testing in the 1950s and 60s, atmospheric tritium spiked. So that's a really, really good indicator. There are these elevated levels of tritium, which are kind of associated with modern post-1960s groundwater. So that's a really nice dividing line between kind of this modern and pre-modern divide. So that atmospheric tritium goes into the rain and goes into the earth, and it's kind of tagged with this, it's a radioactive isotope of actually water itself. So that can be really helpful for this modern, pre-modern divide, which is really around the 1960s. For older, people use carbon-14, which also spiked during nuclear testing, but it has, not to get too technical, but has a different half-life than tritium, and it's been kind of in the atmosphere from natural sources, from solar radiation hitting the atmosphere. So people can actually start dating back with carbon-14 millennia, but the key is actually using a bunch of these tracers in conjunction, because they a lot of them can be used to nail down different time periods. So when you use them all together, they help paint a better picture of the age of groundwater. But there's many caveats and challenges to doing it, but it's something that's a lot of work's been done in.
Okay, this question from John. Here in Florida, we use highly permeable soil columns as rapid infiltration basin and percolation stormwater or treated wastewater reclamation water. Is this an option in California?
Yes, I think I touched on a little bit of it with what we call AGMAR, which is the flooding these fields during the winter. There are groundwater, like dedicated, not agriculture, but there are a lot of groundwater recharge basins. There's an incredible amount of work that's being done in what we call managed aquifer recharge in California. Yeah, so in Florida, it definitely helps because it's very karstic. So it's, for people who don't know what that means, it's like the ground is not like a sandbox, but it's more like Swiss cheese. So water can kind of rapidly pipe in, like kind of think of caves, and that's actually where you get some of these underground, where you get a lot of fast movement of water. But actually, a lot of these managed aquifer recharge operations show pretty quick response at water levels, flooding areas very intensively and just getting water down in there. So that's something a lot of people have been looking at.
Okay, another question. But if you're showing population increase, couldn't some of the nitrate increase be from lawns too?
Yeah, so of course, keeping it simple for the public lecture series, there's definitely people's, especially domestic wells, people's homes, they fertilize their lawns. So that's a source. Septic can also be a source of nitrate, but just the overwhelmingly high nitrate levels throughout the Central Valley have really, you get much higher nitrate levels than you get in other regions where people fertilize their lawns. So, there's some small portion of that are a variety of different nutrient sources and fertilizers, but you just get these whooping high levels in the Central Valley are really have been attributed to agriculture. And we've seen fumigants and pesticides going along with some of these high levels that we know have been used kind of in these big orchard operations and things like that. And we've looked at land use too. So it's definitely a big part of it's the agriculture, but there are other sources for sure.
Right. Another question along that same line as well is, do any of the wells with elevated nitrate exceed safe drinking water standards?
Any other wells?
Do any of the wells with elevated nitrate exceed safe drinking water standards?
So absolutely, and I think I touched upon it a little, but the MCL, the kind of regulatory limit in the Safe Drinking Water Act, is 10 parts per million, and we see whopping high nitrate levels way in excess of 10, 20, 30. Well, that's a lot, and upwards. So in some of the maps I showed, the really dark areas on those nitrate maps, that was areas over 10, over the safe drinking water level. So it's an issue in a lot of these public supply wells when they hit that limit. And we used half of the regulatory limit as kind of the canary in the coal mine. When we said elevated nitrate, we were saying over 5 parts per million. And we did some analysis. Once those wells hit over 5, it's a matter of years before they go over 10, because it's just the leading edge of a big whammy of nitrate that's about to hit it. So it's an issue, and people are drilling wells deeper to try to get around it. But we think that it's moving deeper into the ground the more people are pumping.
Okay. We have a couple questions from Bill Miley. He wants to know, how can farmers better measure the right amount of fertilizers to prevent excess nitrates? Or how about prohibiting crop trees that need a lot of irrigated water and fertilizer to protect groundwater?
So great questions. More focused on policy and management, and actually part of my role as a USGS scientist is I can't really make policy management recommendations. Our role is to provide the best possible science for people to make their own management decisions on how to. But there are other resources, other people working on best management practices in California. So I would kind of point you to those. BMPs, as they're called.
Okay. And one of the other questions, somebody asked, has anyone tried to reenact that famous photo of ground subsidence? It's been 47 years, and it would be interesting to see the change in that time.
Actually, one of the resident experts in land subsidence at the California Water Science Center, Michelle Sneed, has recreated, versions where she's held up, different poles with different levels to show land subsidence. That is one of the most dramatic pictures in the world, in one of the most dramatic areas in the world. It's not like that all over the San Joaquin Valley. And subsidence rates are, that was a time when people weren't really aware of the dangers of Lyme subsidence, and there was a lot so that really, it kind of got out of control at that point in those areas. But yes, Michelle has reenacted that picture.
Yeah, and I will also mention to people, if they're interested, Michelle did a very good talk on groundwater subsidence in California, and it's archived, so you can go back and watch it. Let me see. Hang on, we got a bunch of new questions here. Mostly dealing with irrigation type stuff. Have you studied the impact of injection wells on water quality, especially in relation to dry, wet cycles you described?
Impact of what wells did you say?
Injection wells.
Right. Not specifically in this study. There has been, I think I actually saw a recent study of UC Davis focusing on that, actually just coming out in the past several months. So you might want to look. I think Graham Fogg has done some work on that. But that's a really good question. And, again, I think it's important to look. This is a highly managed, highly human impacted system. I think that's a really important point here is, we think of groundwater as going younger and older and older and older as you get deeper, and how that it's a very static picture of groundwater. But really, I think what our study did show was that, this is a highly pumped system, so it's highly perturbed. So you can get a lot of movement of water that kind of doesn't match what you might expect from first principles hydrology. And injection wells are likely part of that story because they're bypassing a lot of that young water, and they might be impacting deeper water. So there's a lot going on.
Okay. Could you tell us in the response of rain, could you tell us the response of rainfall and in water level, how long it takes to see a rise in the groundwater level? So it's kind of, I guess he's asking about the recharge rate.
Yeah,
for groundwater.
It certainly varies. Obviously, where groundwater levels are really, really deep, it takes a little longer for the water to percolate down. But based on the analysis of water levels we did on a regional scale, you see those water level rise. I showed that plot. It was like wet, and then within the next, then you start to see the water levels start to rise pretty much at the start of the wet year, and continuing to rise for the next few years during a wet period. So there is, when we zoom all the way out, there's a pretty quick response. And I think this also might have to do with how managed a system this is, and how much irrigation water is layered over the landscape during wet times. It's not just precipitation. People are flooding fields with water. So it's getting down in there.
Okay, the last question. Are non-agricultural areas, i.e. city water supplies, lowering their aquifer levels due to extreme drought? And does it affect their water quality?
Yeah, absolutely. The huge piece of the pumping pie in the Central Valley is the agriculture. There's an enormous amount being pumped out. But during dry periods, these public supply wells are pumping a lot to service big populations, and, people need their water, and they need to water their lawns and all kinds of things. So the urban pumping, these clusters of public supply wells in urban areas definitely affects. We've definitely seen lowered water levels there during droughts, even just seasonally. Between the winter and the summer pumping season, you definitely see a depression in water levels, both in the agriculture areas and the urban areas. The agricultural areas can have even more pronounced because they're just the quantity. I talked about yield in gallons per minute, and these bigger wells, these agricultural wells, are like the uber public supply wells. They have huge screens and they go super deep and they pump out tons and tons of water. But we're definitely seeing it both in urban and agricultural areas.
Okay, I think it's all the time we have. Or excuse me, all the questions we have time for this evening. A huge thank you again to Zeno for your talk tonight and answering all those great questions that have come in for our audience. Also, thank you out there for joining us today. In case you would like to watch this again or share it with others, Zeno's lecture will be available in about a week or so for on-demand viewing from our website at www.usgs.gov/PLS. You will also find about 180 archived public lectures on that site spanning over 20 years, so be sure to check it out. If you would like to be added to our mailing list so you can receive notices about our monthly lectures, just send us an email, which can be found by clicking the Connect button on the website, and we can easily add you to the list. Finally, we do hope you will join us again next month on March 24th for Matt's talk entitled Hoofing It in the West, Conservation Challenges and Solutions for Migratory Big Game. Until then, thank you again for joining us and have a good evening. Bye for now.